You want your money?
I'm sorry? Yeah, well, I'll get it here in a bit. We need to get going on this because both of us have a fair amount of material. My notes are already up on the website under the resources. Okay, this is not exactly a research paper. Matter of fact, I didn't even put sources on the end like I normally do. But basically what I'm talking from is this paper. And you'll see some of it up here. Plus I'm going to draw a few things on the screen up here. And what I want to talk about today is I want to talk about standing wave ratio, SWR. It's kind of a hot button issue, and it's that way because there's about as much misinformation out there as there is legitimate information. And I wanted to approach this topic from more of a beginner's level in terms of language and whatever, so you're not going to be inundated with a lot of jargon. We are going to talk about some terms. There's no math involved or whatever, but there are things going to be presented today that you're going to need to know, especially if you're at the technician level looking to advance to the general. And I very much want you to do that. HF is a lot of fun, and you're missing out with just a technician license. There's just only a little bit of, what, 10 meters that's available for
300 to
technician?
500. 300 to 500 on 10 meters.
Yeah. And boy, there's just so much good stuff on there. And it's not that big of a leap from the technician to the general. But, again, this is kind of a hot button issue. It's kind of like antennas in general because everybody has opinions, and the human brain, being what it is, tends to fill in gaps in stuff that we don't know or understand, especially in the physics or the math or whatever. And it's not uncommon to build a whole mythology around something. I could very easily become an evangelist for in-fed half-wave antennas, and they are not the end-all be-all antenna. They have their place. But I could create this whole thing. It works so good for me, it's going to work good for you. I could really develop a lot of pathos for that. And a lot of stuff with antennas is that way. So I want to clear up some of the stuff about SWR and what it is and what it is not. And I'm going to start by talking about what it is not. Standing wave ratio, which is a measure, and we'll talk about what it is in depth there in a minute. It is not an indicator of how efficient your antenna is. That's not what it's about. And that's one of the common myths. Having a low SWR, which is the desirable way to go, is not an indication of how well your antenna system is going to work. $1 billion idea. Invent something like an antenna analyzer that can actually measure the efficiency of your antenna. I've tried field strength meters, but it gets a little movement on the needle.
Hold that thought for later.
Yeah. But being one of the last areas of amateur radio that we can get in and diddle with ourselves and adjust, SWR became a very big thing. And it started even back in the CV days. So there's been a lot of hype about it, but it is indeed an important measurement, and it's something that you should be tracking in your radio station, because it will give you an indication. Antennas age, and they're infected by the first rule of antennas, as Woody oftentimes says, and that's where I got it from. When it comes to antennas, everything affects everything. Okay, the environment, all of it. Antennas don't age well. So following that measurement, that SWR, is very key. All right, enough preliminary. I think in the words of Plato, if you're going to talk to me, define your terms. So let's talk about a few terms that you're going to need to understand. And I'm going to go through this for the reason of time a little more quickly than I planned. This is up on the internet on our website, so you can download it.
Can we put it on the screen for you there?
Well, we can get to it here in a minute. Yeah, that's okay. If you want to scroll through it, that's good. Okay. So, let's look at, let's try and understand some of this terminology. Just a few words here. And specifically, we're going to be looking at words like resistance, impedance, reactance, and resonance. And at least 3 of those terms sound very similar. They sound a lot like resistance. And yeah, they are. They're related to that. The other thing that you need to know is that we have direct current voltage, that what comes out of a battery, DC systems, and we have AC systems. And electronic components, a lot of them behave differently when they're in an AC environment than they do when they're in a DC environment. One of the exceptions to that is a resistor. Now I've got a little bag of parts here, a resistor, a capacitor, a coil, and a wire. So you can finger that and see what's in there. We'll talk about that. Just something to pass around. You can think of it like one of those spinners to keep you occupied. Okay, so the first thing we want to look at is direct current voltage, usually abbreviated DC. Anybody not understand what direct current means? Okay, it's like what comes out of a battery. It's at a constant level, constant current within the limit of the battery and how it discharges. Then we have alternating current voltage, or just AC voltage. This is like what comes out of the wall. And and that's not quite in there yet. But anyway,
Something like that, right?
yeah, that's a sine wave. Well, several of them, and we'll talk specifically about that graph here in a minute, because that's one of the more interesting things. Now, radio frequency signals are AC signals. They're not DC. RF is AC. I don't think there's any place where it's anything other than AC, do you? Can't think of anything.
Except the power into the radio.
Yeah, okay. So we're looking at RF.
Yes, sir.
RF gets to be kind of a strange animal to start with, just by the nature, the physics of RF and how it's generated and so forth. How it propagates. That's the closest thing to magic there is. You know, anything in the electromagnetic spectrum, which is where RF is, way below visible light in terms of wavelength. And it has a magnetic and electrical property. Okay. Resistance. Resistance, and I'm not defining these as an engineer or even an electronics guy necessarily. This is my own take. Resistance is the opposition to the flow of electrons in a DC circuit. Well, it turns out that resistors behave pretty much the same way even in an AC circuit. They're one of the few components that don't react to the RF AC. But resistance, when somebody's talking about the resistance component in an antenna system, we're talking about pure DC resistance. Okay. So now we get into the area of those components that do react or behave differently in an AC environment. That opposition to the flow is called reactance. And when we're talking about antenna systems, we're talking about 2 specific components. We're talking about inductors, coils. That's like that little coil of wire that's in that bag here, that's red thing. Here, this is an inductor. And capacitive reactance. So reactance is simply a term for resistance, but in the AC environment. The next term is impedance. Well, isn't resistance and reactance enough? No. Bundle the 2 together. Put the DC pure resistance in with the inductive and capacitive reactance, and you have the total, which is called impedance. And that's the term you probably hear more often because we're talking about matching impedance all the time. And that's where SWR, standing wave ratio, comes in. It's really VSWR, voltage standing wave ratio. There are other more complications to that, but that's basically what it is. So impedance then is the opposition of the combination of resistance and the opposition that's offered by inductors and capacitors to the flow of our RF signal. Now, why is this good or bad? Go back to that one where the thing is flopping around. Let's get to the nature of the beast. Okay, this thing that you see moving around. First of all, if you notice, we have a blue. You might not be able to see the color, but the fainter blue one. The peaks appear to be heading from left to right. This is the source off to the left. This is your transmitter. It's putting out the RF signal down there. And notice that this red one appears to be headed back. When that source signal hits impedance, that signal, or part of it, gets reflected back. So some of your RF energy that you would like to go to your antenna system doesn't get there because it's being reflected back by impedances. Now, it turns out, and if you watch this closely, when the blue and the red peaks get together, you'll notice that this black thing that appears stationary, wiggling up and down, this thing gets created by those other two waves. This black thing in the middle of the screen, that is a standing wave. That's what it looks like. It looks like it's stationary, just going up and down in one spot. And it can get bigger because as the two peaks coincide with the reflected and the source signal, it causes that standing wave to increase in voltage, and that voltage, in a severe enough impedance mismatch, can be enough to fry the outputs in your transmitter. So yes, SWR, standing wave ratio, and I'll talk about what the ratio is here in a minute, is very important to follow and measure. Okay. The last term, go to the one that looks like that. Yeah. The last term I want to talk about is resonance. And this is a little harder to get my mind wrapped around a little bit. I really like it. I like the idea of resonance, what it's about. It's kind of another magical thing. Ideally, we want, I skipped over the main thrust here. The idea of measuring SWR and getting an idea of what that number is tells us whether we need to improve, fix, or whatever to our antenna system. What we want is we want to have the impedance of the impedance of most radios today. The output impedance is 50 ohms. And our cable, there's a coil of RG8X over there someplace. Most of us are using coax, but you can use other things as well, that go from the transmitter and connect to the antenna. Okay, this cable is called feed line or transmission line. And it also has an impedance, coax anyway, that we use, typically has an impedance of 50 ohms. So now we've got a match between the radio and the cable, and we need to worry about what the impedance is of the antenna system. See, there's three components there: the transmitter, the feed line, and the antenna system. If we can match those impedances so they're all equal, then we're dealing basically with just the pure resistance to the signal. We get the maximum transfer of energy from the transmitter to the input of the antenna system. Now, what the antenna system does with that energy is dependent on the design of the antenna and the efficiency of the antenna. Matching, getting this matched, this SWR ratio down to 1 would be perfect, okay, or something close to that. Gives us the maximum transfer, but it has nothing to do with the efficiency of the radiation of the RF energy off the antenna system. And here's proof of that. Everybody know what a dummy load is? You know, it's a gizmo with heat fins on it and whatever, and you can screw it right into the back of your transmitter, and you can transmit into it so your signal is not going out into the air. If you do an SWR measurement, it's 1-to-1, it's a perfect match. But there's no radiation of RF energy into the air.
It's basically a resistor, isn't it?
There's just a big resistor in there. Well, ideally, well, not ideally, typically, and then this is a series, this doesn't have the R in it, I have one of those someplace, but an antenna system looks like a combination of inductors and capacitors, and there's also a resistive component to it. So that's kind of what it sees. Now, resonance occurs. Remember, resonance, if you remember nothing else, resonance is the point where both the inductive resistance, I'll use that word resistance, the inductive resistance and the capacitive resistance equal each other. What happens is one is the opposite of the other, they cancel each other out. And all that's left is the pure resistor part, which is 50 ohms, and that's what the feed point of your antenna should be, or whatever. But the point is that it's at this point of resonance. The capacitive one is the red one coming down, the inductor is the blue one going up, and this is where they are resonant, and this would be the frequency. Now, where that occurs is frequency dependent. It changes based on what frequency you're dealing with. Inductors build up a magnetic field as the signal pulses. So we got this field growing and collapsing, and as we go up in frequency, that has to happen faster and faster and faster, and physics says, no, there's a limit here, we're not going to let you speed here. So impedance, inductive reactance goes way up. Capacitors are just the opposite. The higher you get in frequency, the more the capacitor looks like a dead short. So all of its reactance is at the lower end. The point is, and all you really need to remember, is the two cancel each other out. So if you get one equal to the other, right there we have resonance. The other area where resonance enters in, just to kind of finish that point off, is we can cut our antennas or tune antennas so they are resonant for a particular frequency, but that's a different thing going on, okay?
That's what I was going to ask Todd. So, when you have your antenna, do you have a little dial to adjust that? And the answer is no. You do that by changing the length of the antenna. That's what Todd's talking about, trimming your antenna.
Okay. Now an antenna can be tuned to a resonant for resonance on a particular frequency. For example, an end-fed half-wave dipole might have its radiating element cut to be a half-wave in the mid-band of 40 meters. That's what mine at home is. And because of harmonics, I not only get 40 meters, it becomes a multi-band antenna. I not only get 40 meters, but I get 20 meters and 15 meters. and if you put a little cap in there across the input to the, so I can get 4 bands. But it's always at the sacrifice of efficiency, all right? In a perfect world, you have an antenna that's tuned exactly for the frequency you want to operate on, but it's only good for that frequency. And of course, that's not very practical. So most of us want to operate on more than 1 band. All right. Any questions about what reactance is, impedance is, resonance? All right. I've already talked about what SWR, standing wave ratio, is not. So what is it then? Ratios are fractions, fractions are ratios. So we have a numerator and a denominator. That wave, go down, there's another one of those down a little further. Yeah, there it is, right there, okay.
Sorry.
SWR, this one I liked because it is marking the standing wave at its maximum voltage and at its minimum voltage. SWR is the ratio of the maximum voltage divided by the minimum voltage. And I do a little calculation a little further down. Well, I use this one. This one has a maximum voltage of 1.5 volts, a minimum voltage of 0.5 volt, and if you divide 0.5 volt into 1.5 volts, you get an SWR of 3. That's 3 to 1. Most of us would not operate our transmitters with a mismatch of 3 to 1. You're about at the limit of what would be good for the transmitter. Fortunately, most of modern transmitters today also have protection circuitry in them for high SWR. So you're kind of protected, but you should know what your SWR is. So that's the ratio. That's where it gets its name. Standing wave, that's this blue one going there, and it's the voltage, the maximum voltage divided by the minimum voltage. So that's as mathematical as we're going to get on a pad.
Yes, sir. Can you get a could you get a false reading?
Oh, absolutely. I've seen cases, and as a matter of fact, I did it myself. I picked up a whole bunch of R8 coax, 75 feet. Some of it belonged to the club, some of it belonged to the person I got it from, or whatever. I was happy to get it, strung it up there, and man, I had great SWR 1-to-1 out there, and the cable was no good. It was long enough, it just absorbed everything, and it definitely get a
So
false.
how would you know if you got a false reading versus, you know, hey, well, how would you know that?
I don't know of a direct measurement to do that, because like you say, about the only thing I have available is to put an antenna analyzer on there and tell me. But what I was going by was the performance. I should be hearing signals, I'm not hearing anything, nobody's picking me up, and yet I supposedly have, you know, a good antenna system. That's why I say we need that gizmo that somebody can stand out there next to your antenna and give you a rating on how effective, you know, how much RF energy it can actually throw out into the atmosphere.
I have one suggestion on that, what Pat asked. If you measure the SWR on your antenna and it's almost flat on all frequencies, it's junk.
Ah, good point. Good point. I should have thought of that.
You want to see it going up and down.
Yeah, exactly.
It's basically a resistor then. It
Yeah.
shows-
Yeah, pretty much.
Yeah.
But it can swamp out, you know, problems. It can make your antenna system look like it's good when it's really bad. So yeah, do some further checking. And that's where I really like the little nano VNA, because you can plug that in there and get the, well, you can get the same thing off the Rig Expert. You can see if you sweep the frequencies from say, okay, I'm gonna operate from 40 meters to 10 meters, and I put those frequencies in there for the analyzer to sweep. You plug your antenna into it, and the analyzer sweeps the cable, puts those frequencies out, and then plots where the dips are. And you should see dips where you expect them, for what your antenna is designed for. And if you're getting flat matches on everything, yeah, that's, red flag should go up.
You lost me on that one part. You're saying that it goes up a certain height for to get the ratio. You were saying if the peak was something, wouldn't, it looks like they're going up and down, so wouldn't the peak be like minus,
if
like
you-
1 and -1, or?
No, the actual 0 point is right here in the middle, okay? But if you watch the peak, this peak only comes down. You have to watch where
On
it
the
drops.
blue one?
Not the
Are we
bottom
watching?
part of the peak, but the top part of the peak. It rises to 1.5 and drops back down to half.
Is that the blue one?
Yes, that's the blue.
It looks like it's going below that though.
I'm sorry?
It looks like the blue line is going below the half.
Well, if you follow it all the way down, it does, but just watch the one peak. Just watch what this one peak does.
Oh,
It's a little hard to catch. And I don't know if that's actually what's happening inside the wire. This is a model, kind of a representation. Okay. The important part is that the tester, the analyzer, has the ability to get these voltages. But you need a gizmo, a piece of test equipment, like a rig expert, or a nano VNA, or some other make of antenna analyzer. Well, I say that. Now, most radios today, I know the last couple I've got, the S meter in the radio also has a function where it will show the SWR. So you may not have to go out and buy one, but if you fiddle around with cables and antennas, and I like to swap stuff out, build my own stuff, so I like to get a little more in depth on the analysis.
Now, is that mostly HF rigs, or do the VHF rigs?
I don't know about
Some
VHF.
some have it, and sometimes it's just a light, sometimes it's actually a, it just depends on the radio.
Yeah. And some analyzers have two antenna tuners. I brought an old manual tuner, and you can see, and the reason why I brought this, you can pass this around. If you look at the knobs, you'll notice that it's all about inductors. It doesn't say capacitors, but the transmitter, if you were to open that up, there's a big old wire air core coil in there with taps off of it, and then there's tuning capacitors in there. So that's what these tuners are doing. They are adding capacitance and/or inductance to the system to match, to get these impedances matched. Think of it this way. You got a big old pipe. I think I could draw this.
Yep.
You got a big old pipe here, and you got RF coming down here, maybe it's water, and you got another pipe here. This is the feed line that goes out to the antenna. These are not matched. What you're doing is you're stuffing this down here so it's exactly matched. You're getting the maximum transfer of RF energy through the feed line system to the input of the antenna system by having the impedances matched. That's the goal. You want as much RF energy out to your antenna as possible. And then it depends on the efficiency of your antenna and of course propagation properties as well. There's a big mix. And again, I'll end this by saying, when it comes to antenna systems, everything affects everything. So trying to measure some of this stuff with the antenna in place is problematic at best. But it can be done. There's some functions on the nano VNA, and I think even the rig expert, where we can get some of that stuff.
I just want to go back real quick. You were talking about the analyzers and using analyzers and then the one in the radio. It said that you should test your antenna at the antenna, as close to the antenna as you can. rather than at the radio, but you can test your coax, of course, through that. But that's one of the reasons of having a handheld type nano VNA or rig expert, is to test it at the antenna rather than at the radio.
Sure. That's another way to find out if the cable is junk or not.
And you'll also see the guys who do this a lot, they'll run the analysis and they'll walk away from their antenna because just standing next to it changes your reading
Everything affects everything.
to a significant degree.
It does. It does. It's amazing what has impact on that whatever. They're sensitive. They're like little 2-year-olds or something. in a snit.
So, what would you consider to be what would you consider to be like a minimum okay SWR?
I'm so glad you asked that question. So glad you asked that question. This is part of the mythology too. I've seen people obsess over getting 1-to-1, getting that perfect reading. The rule of thumb, as best as I can determine, and you shouldn't trust my credibility more than anybody else's. I mean, I've gone through a lot of material and tried to synthesize it down to what I see as the truths here and present that. But I'm not an electrical engineer or whatever, so you know, my job when I worked back in the world was doing software. You know how software guys are. Anyway, it seems that the current rule of thumb is 2-to-1 or less, or say less than 2-to-1. That's the rule of thumb. Most radios can handle that with no problem whatsoever. And let's say you're putting it, what does that mean in the real world? Okay, I got 2-to-1, my gosh, you know, no. 100 watts, you're losing about 10 watts if you have a 2-to-1 match. So you're putting out, you're radiating 90 watts instead of the full 100. And that's going to be barely noticeable on the other end, depending on where the thing is going. So obsessing over trying to get a 1.5-to-1 down to 1.2, there's no return on investment in doing that. It's not going to be noticeable. I mean, you might want to do it just because, you know, like me, maybe you're anal that way. I don't know. But I like to see it as low as possible, but most of that is an emotional thing and not based on the physics. Bruce?
Just to go on with what he's saying, we throw up a dipole antenna. It's going to be 75 ohms impedance. You can look it up. We're running a 50 ohm coax into the 75 ohm. We got a mismatch to start
Exactly,
with. You know,
yeah.
We're already at 1.5, 1.5 to 1 to start with, and most of us don't even care. That's great. We're hunky dory. So he's right. Don't worry about the little nit.
And before the solid state output transistors and finals, you know, tubes were used, and tubes are still used today in some radios and certainly in some linear amplifiers. Tubes were able to absorb this difference without, nobody even cared about SWR. You know, hook it up to a pair of bed springs and you know, a couple of Pontiacs bumper to bumper, broadcast away. All right, I want to say one last thing, and that is, most of my information nowadays comes from what you guys, a lot of you refer to as YouTube University. There's a huge amount of information. It's great out there, but boy, you can get lost, and anybody can post anything they want out there and say that it's the truth. So verify the stuff. You know, don't be afraid to check out. I go to various websites and there's a lot of double E schools and courses and stuff out there that have some of their course material. So I try to validate the material as best as possible. All right, that's really about all I've got on this. Like I said, I got a couple of schematics down here of what a cable looks like in terms of components, inductors and capacitors, and what an end of the antenna system might look like. And you can, yeah. It's not great, but yeah, it is what it is.
Electrical Engineering 101.
Huh?
Electrical Engineering 101.
There you are. Exactly.
I think it's
All right, any other questions about standing wave ratio? Okay, 2 to 1 or less, you're fine, don't even worry about it, but follow it, check it.
I'd say one comment, look in your manual on your radio, it'll spec. Don't go over or keep your SWR, this much or less, okay? 2 to 1's cool, whatever, but I mean, your radio, if you got a solid state radio, I wouldn't be doing 2 to 1 in a solid state radio.
Well, they have protection circuits, and you
Yeah,
will see
you
your
assume,
power
you
meter
assume.
showing a drop.
Again, but that.
Well,
that's not-
Felix does have a point, and a lot of the new radios, and I have a new Yaesu FT 710, and it has a tuner built into it. But I don't think it's very good. It's kind of, it's an entry-level radio cost-wise, and I don't think they put a lot of money in the tuner. It's not as good as some of the tuners built into the others. So I use an external tuner. I turned it off. But it supposedly will handle anything up to 3 to 1. But I'm with Felix. I don't like it over 2 to 1. Or whatever. I try to keep it low. And most of the time I'm operating. I have an end-fed half wave that's cut for 20 meters that I do for POTA, and I don't even use a tuner. John and I went out in the park one day and with the Nano VNA, and we trimmed that antenna, because I put it up as a sloper. We trimmed that antenna so that it's matched. I don't even need a tuner. And the SWR meter on my POTA radio, I think the worst I've ever seen is 1.5. And I'm happy with that. So is the radio. Make tons of contacts.
Just Woody, where on the web, I was gonna show on the website where this is gonna be found.
It's under resources.
Under resources.
It's under resources, go to general resources, yep.
Yeah, general resources.
And then scroll down. Todd put it down below some stuff that he already has on there.
Yeah.
It's at the bottom of his link.
Antenna links.
Antenna links, yeah, here it is.
Here it is right there.
Yep. And there's also Todd's presentation on NFED half-wave presentation.
Yeah, and I want to do a version 2.0 on that, because there's been enough changes to the NFED and what's being done. So look for that upcoming. Maybe we'll get that in this year.
And this video will be linked right under that, and it'll be on YouTube. Thanks, Todd.
Oh, yeah.